Hi all, welcome to discussion on time-dependent perturbation theory. Today we'll just give a brief introduction about time-dependent perturbation. So time-dependent perturbation usually happens if the Hamiltonian takes the form h0, which is a free part, plus a perturbation part, where the perturbation part is a function of time, and the total Hamiltonian is a function of time. H is a function of time. H0 is time independent. Independent part of the Hamiltonian, and which is completely solvable. Okay, where V of t is a perturbation. So then we can apply the perturbation theory, the time dependent perturbation theory, provided the V of t is much less than h0. Okay, so before going to the exact time dependent perturbation theory, we should have a overall idea about the interaction picture, because we are going to use the interaction picture to solve or to use the time dependent perturbation theory, to apply the time dependent perturbation theory. So the first of all, we should know the interaction picture, and the interaction picture we already learned in the previous semester. Okay, so I will just revise a few important points about the interaction picture. Okay, so basically in the interaction picture, if the Hamiltonian of the system has two parts, a free part and a perturbation part, then we can define the state and the operator in the interaction picture as follows. The state of the system, psi of t, in the interaction picture is defined to be e raised to I h0 t by h cross and psi of t. Simply the psi of t means the state in Schrodinger picture. Okay, then correspondingly the operator A in the interaction picture, it must be function of time. So in the interaction picture, both the state vector and the operator are the function of time, and that can be written as e raised to I h0 t by h cross the operator A, which is the operator in the Schrodinger picture, e raised to minus h0 t by h cross. Okay, so these are the state vector and the operator in the interaction picture and its connection with the Schrodinger picture. Okay, now we can write the equation of motion for the state vector. The equation of motion for the state vector will take the form IH cross dou psi of t I by dou t. This subscript I represents it is an interaction picture, and that would be equal to V acting on psi of t I. Okay, and similarly the time evolution for the operator can be written as IH cross dou AI by dou t is commutator AI comma H0. So these things we have already learned during the different pictures in quantum mechanics. Okay, and we have to use this information while we are applying the time dependent perturbation theory. So not that we have not started what is time dependent perturbation theory till now. Okay, now we can start the formalism of the time dependent perturbation theory. So the formalism. of time dependent perturbation theory. So how to start about it? Okay. Now we already noted that the time dependent perturbation theory is applicable if the total Hamiltonian is split into two, a free part which is h0 and a time dependent part v of t. Okay, now let us assume this h0 is a free part, and there would be the corresponding state vector for it. So I will denote by symbol psi n. So h0 psi n. So psi n are the eigenvectors of the operator h0. Corresponding energy is En psi n. So what is this psi n? So psi n is basically the eigenvectors of unperturbed part of the Hamiltonian. So I can call this h0 is the unperturbed part. That is, when v of t is absent, the total Hamiltonian is simply h0, and v of t is a perturbation part. So hence psi n, I can say that it is the energy eigenstate or eigenstate of the unperturbed Hamiltonian. So well and good. Okay. Now, if v of t is present, then what would happen? So here we are going to apply one condition, that is this v of t is not present at all the time. The v of t is present for small amount of time, maybe from 0 to tau, and v of t is absent for all other duration. Okay. So I am assuming this v of t is non-zero. The v of t is same as v of t for the time 0 less than t less than tau, and it is 0 otherwise. Okay, so the choice of tau is up to you. The tau can be very small in number and tau can be very large in number. So in general, the v of t is present for an interval between 0 to tau, and it is not present otherwise. So what would happen till the time 0? The total Hamiltonian is only h0, and hence the state of the system may be in one of the energy eigenstate of h0, or maybe in the superposition of h0. Okay, so that means the state of the system will remain same forever if the perturbation part is, if there is no perturbation, and that is well known to us, because if psi n are the energy eigenstate, what about the time evolution for the energy eigenstate, the psi n of t? I can write it is according to the Schrodinger picture, is e raised to I or minus I h0 t by h cross psi n at a time 0. And this can be written as e raised to minus I e n t by h cross psi n at a 0. So that means the state of the system, the psi n, remains as psi n in the later time also, because this is only a phase factor. This phase factor does not change. Okay, so basically what is important is the norm of the state. So sine of t, the inner product sine of t is same as sine of 0, sine of 0. So the norm of the vector does not change. So hence there is no much importance for this the phase factor. So the thing is in the Schrodinger picture, if the state of the system is in the one of the energy eigenstate, then it will remain forever. So I think if you want to, if you need more clarity, then we can have a simple system to get a more idea about it. So consider a two-level atom. A two-level atom. Okay, so a two-level atom. So two-level atom means it has only two energy levels. Okay, so a ground state. So ground state we can denote it as G, and excited state we can denote it as E. So ground state will have energy Eg, and excited state will have energy EE. Okay, that's good. Now, suppose the state of the system at time 0 is equal to E. Okay, so initially assume the atom is in the excited state. Then what would be its state in the later time? So according to this from the picture, so we can find the state of the system the later time as e raised to minus I h0 t by h cross acting on psi at 0, and this would simply give e raised to minus I e t by h cross, and psi of 0 is simply e. Okay, so the state of the system will remain as e, but there would be a phase factor. Now there is no much importance for the phase factor. The thing is, suppose if you find the energy of the system, okay, suppose the energy, how will you find energy? You have to act the Hamiltonian. So you have to, if you act the Hamiltonian H0 at psi of t, what will you get? It will be e raised to minus I e e t by h cross. So this is a constant. Then H0 acting on E. And what would be H0 acting on E? That would give the energy EE times the state E, get E. So this would become the energy E raised to minus I EE T by H cross acting on E. So this would be EE times. Okay, so the energy E, that is basically psi of t. Okay, so there is no change in the state. The state remains same. So here also H0 acting on psi at 0 is excited state energy into psi at 0. Okay, so there is no change in the energy. So that means if a system is in the energy eigenstate of a Hamiltonian, then that system will remain forever in that particular state. Only thing is it will have an exponential phase factor, and there is no much importance for this exponential phase factor, except in certain cases. That is when you are dealing about the Berry phase and all, the geometrical phase, then the phase factor matters. Otherwise, usually this exponential phase is a dynamical phase, and there is no much importance for it, and that only gives the time evolution, that only represent the time evolution for the state. So this says that if the atom is already in the excited state, then it will remain forever in that state. That means the atom will not undergo any kind of spontaneous emission. Okay, but we know that there are spontaneous emission for the atom. So because if the atom is in the excited state, it cannot stay forever. It may de-excite, and we may get radiation and all. So that we know, and that would happen only if perturbation is present. So if the perturbation is present, that is if the total Hamiltonian, so if the total Hamiltonian is simply H0, then this is the case. But if the total Hamiltonian is H0 plus some perturbation, then there is a possibility that the atom may de-excite and we may get some radiation outside. Okay, so there may be emission of some energy. So that would happen if this is present. Okay, so the basic idea and the basic principle behind this time dependent perturbation theory is to check whether it is possible to undergo any transition. So remember, this V of t, the strength of the V of t would be much less than H0. Okay. So hence, therefore, the presence of V of t will not create new possible states. Okay. So we are just restricting uh, the production of new degrees of freedom in the presence by the presence of the perturbation part. However, the presence of perturbation may influence the system to undergo a transition. Okay, so I will repeat once again. So if the total Hamiltonian is simply H0, then there will not be any much transition to the system. The system will remain forever in its initial state. But if there is a perturbation, and if the perturbation is much less than, the strength of the perturbation is much less than the free part of the Hamiltonian, then what would happen is, the first thing is, the presence of perturbation will not make any new possible configurations. It will not make any new possible states. And the second thing is, the presence of perturbation may initiate transition. The system may change from one state to the other. Okay, so if V of t is much less than H0, then the first thing is no additional degrees of freedom. So that means the Hilbert space of the system will remain same. That is, Hilbert space of the system will remain same. So not that this is not applicable always. Suppose in certain cases, what may happen is, if you have a perturbation, very strong perturbation, then we may have to introduce a new degrees of freedom like spin. Okay, so initially we may not consider the presence of spin in the free Hamiltonian, but if we apply very strong perturbation, for example, very strong magnetic field, then we that strong magnetic field uh, can cause to use the degrees of freedom like spin. It may induce a new degrees of freedom. So such things may happen. But if the perturbation is very small, then usually will be safe. And so we are restricting our discussion with no additional degrees of freedoms are produced by the due to the presence of perturbation. So that's the first part. And hence we can use the same Hilbert space. So there is no need to you introduce a new basis states and all. So we can use the basis states of H0 as the complete basis. Now the second thing is, so since there is no addition states are produced, the presence of perturbation may initiate transition of state. So that means the system may undergo a transition from one state to the other. Okay. Now how we can use this? So usually what you have to do, we have to use we have to solve the Schrodinger equation to find the time evolution of the system. Okay. So if the total Hamiltonian is H0 plus V of t, then what may be the future state? How will you do? You have to use the Schrodinger equation. We have to solve the Schrodinger equation. What is the Schrodinger equation? Schrodinger equation is IH cross the psi of t by dot t equal to h, and what is h? H0 plus V of t, the psi of t. Okay. So if you can able to solve this, then we'll get the time evolution. Okay, and we may come to know that what is the transition probability and all. Okay, but this direct solving may not be possible always. So how will you do it? So for that we have to go for the approximation method. Okay, now so we can go to the approximation method. So first of all, we should have a general formalism for it. So what you can do is we can expand this psi of t. So expand psi of t in basis states. So the basis states are we can use the complete set of eigenstate of a Hermitian operator as a basis state. So here I can use the energy eigenstate of unperturbed part of the Hamiltonian as a basis state. So I'm representing psi n as the unperturbed the eigenstate of the unperturbed part of the Hamiltonian. Okay, so then I can expand my psi of t as sum over n c n of t e raised to minus I e n t by h cross psi n. Is it okay? So what actually I have done? So what actually I have done is the psi of t in general we can expand as some cn psi n. Psi n is a function of time. And how can I write psi n of t? Is equal to cn e raised to minus I e n t by h cross psi n at 0. So this is what I have done here. And this cn is expansion coefficient. Now since our v is a time dependent, or total Hamiltonian is a time dependent function, so that is why I have included a time dependence on the expansion coefficient. Okay, so I have not done much thing. So basically this is the expansion of the wave vector in the basis state. Okay, and the basis states itself can have a time evolution, so that time evolution is written here. Okay, so that is a normal time evolution. Now apart from that, here the Hamiltonian also changes with time, so there should be that connection should come into this the state vector. So that is why I have introduced a time dependence for Cn. Okay, so I think it is clear to you. So I can expand the state vector, the psi of t, which is comes in the Schrodinger equation with the complete Hamiltonian, which is 0 plus v of t as sum over n cn of t raised to minus I e n t by h cross cn. Okay, so this is one important point. So if the Hamiltonian is time independent, if the total Hamiltonian is time independent, then there is no need to attach the time dependence on this expansion coefficient. Okay, so Cn of t, I have given uh, the time evolution, a time dependence to this expansion coefficient only because the total Hamiltonian is function of time. Okay, now we are going to apply the interaction picture here. Okay, so in interaction picture we already know what is the form of the state vector. So state vector psi of t in the interaction picture, how can I write? Basically e raised to I h0 t by h cross and psi of t, which is in the Schrodinger picture. Okay, now in Schrodinger picture, state vector can be written as u t t0 psi at t0. Okay, so this is known to us in Schrodinger picture. The time evolution of the state vector can be represented using a unitary operator. Okay, so this is basically a unitary transformation. The time evolution is shown in the picture is a unitary transformation. So hence this can be written as e raised to I h0 t by h cross u t comma t0, the state at t0. Okay, now this is in this Schrodinger picture. Now how can I convert the state in this Schrodinger picture into the interaction picture? Just do the opposite of the first line. So e raised to I h0 t by h cross u t t0. Okay, so the same line I have written here. I am going to change psi at t0, which is in the Schrodinger picture. I am going to convert this state into interaction picture. So then it's become e raised to minus I h0 t by h cross the state at t0 in the interaction picture. Okay, so this is what happened is here we have got a connection between the state of the system in the interaction picture from one time to the other time, from one time to the other time. Okay, so this gives the time evolution for the state in the interaction picture. So the state of the system at time t in the interaction picture can be written as some ui t comma t0. So at t0 I. Now what is ui? So ui t comma t0 is e raised to I h0 t by h cross u t comma t0 e raised to minus I h0 t by h cross. Okay, so once you know ui, if you know ui, I can find the state of the system in the interaction picture at any time t. Okay, so once we know ui tt0, we can find state of the system at any time t in interaction picture. So that's all. So now our question comes to this point. Now in order to know the state of the system at any time t, just thing is I want to know the structure of ui. Okay, so not that till now I have not used any kind of approximation. I have just formulated, I am going to formulate the time dependent perturbation theory. So this kind of thing is applicable in without any approximation. Okay, so all these are valid without any approximation. I have just re-expressed the interaction picture in another form. Okay, so we can summarize what we have discussed till now. Okay, so we know that in order to use the time dependent perturbation theory, we should know the interaction picture. We have just revised all the important equations in the interaction picture at the beginning. Okay, so this equation we have already used. We'll use it. And the time dependent perturbation theory is an approximation method, and it is usually applicable if the total Hamilton has two parts, a time independent part which is exactly solvable and a time dependent part which is called perturbation, and the effect of the time dependent part must be very small compared to the time independent part, the h0. And since h0 is completely solved with the h0, the eigenstate can be called as the energy eigenstates and represented by symbol psi n. and the psi n set psi n forms the complete basis, because psi n are the energy eigenstate of the unperturbed part of the Hamiltonian, which is the Hermitian operator, and can be regarded as the complete basis. Okay. Now I am assuming few things here. The thing is the v of t is much small, and it is for a small amount of time from 0 to tau. Okay, and it is 0 otherwise. Okay, so since v of t is very much small compared to h0, two implications for it. One is it will not produce any additional degrees of freedom, so there is no new possible states are produced by the presence of v of t. So all the states would be, all possible energy in state would be the eigenstate of h0, and only thing happens by the presence of v of t is a system can undergo a transition from one state to the other. Okay, so if such perturbation is not present, then usually the system will remain in the initial state of the system. Okay, there will not be any much time evolution for the system if there is no perturbation, and we have illustrated using one example, the two-level atom. Okay, now in order to find the transition, that is what would be the time evolution of the state of the system by the with the presence of the perturbation, we have to solve the Schrodinger equation, and the solving Schrodinger equation is not easy. So we will use the other way. The other way is what I will do is I will express the state vector in another form, in another picture, the interaction picture. Okay. So the first of all, what I've done is I've just expanded this psi of t, and we can write the psi of t as c n of t raised to minus I n t by h cross into psi n, and that let it be there. We will use it later. Okay, and the state vector psi of ti in the interaction picture, the psi of ti I can write as u I t t0 psi of t0 I. Okay, so I can connect the state vector in some time t0 to the state vector at time t in the interaction picture through a new operator ui, and the ui is connected with the u in this form. So once you know ui, you can find the complete time evolution for the of the system. So that is the main idea we are applied here. Now the next thing is we'll use this technique, and we'll apply the perturbation theory to find the expression for ui, and thereby to find the future possible state of the system and the transition probability. Okay, so that's it for now. So we are stopping it here. So in the next lecture, we're going to discuss how to find ui by the approximation method. Thank you.